Okay, so this is the last lecture. So I will go on to the other two questions that I had mentioned. So I will skip this business of what I had mentioned about Carlin McGregor and Lindstrom, Gezelviano, whatever. So what I will, but before going to there, let me say one last thing about this long-term behavior, something which may have come up in this lectures. I didn't see very much if anybody was talking about expander graphs and stuff like that. But let me just mention one thing. So what we saw is that, so let me just do a small thing about, I won't actually prove much, or maybe I'll prove one thing, but it is to tell you about something. Okay, so more like that. So again, let's take x to be, so s is finite, and p I take to be irreducible and aperiodic. So we use those words for the Markov chain or for the transition matrix. So irreducible and aperiodic. Let's just take it to be that. Irreducible and aperiodic. And then let's take, okay, one small point to note, since somebody asked, so Rajesh asked about reversible. So there is something, so we know that p to the t I comma j converges to pi j, where pi is the eigenvector for P transpose. P dagger pi equal to pi. Okay. So pi is this, if I write it as a column vector, then it is the eigenvector for the transpose of the transition matrix with eigenvalue 1. Okay. So there was a special, first let me say something. So now let me say, I'll say a few things about reversible case. So what is this business of reversible? Another point about reversible, which I did not mention earlier. So reversible means pi I Pij equal to pi j Pji for all pairs of states. Okay, so you may recall that the way I defined reversible was, we said there are some number sigma such that this happens, but then we saw that that sigma is basically pi after normalizing pi. So pi also satisfies the same. If you multiply sigma by 2 or constant, it will not change this equation. So any multiple of sigma will also satisfy. So pi satisfies. So a Markov chain is reversible means pi I Pij equal to pi j Pji for all ij in S. So here is one thing I want to say, which is just to, so that you know this. So reversible chains are very special. Reversible Markov chain is same as random walks on weighted graphs. Okay. So earlier, I'll go back to that page and show instead of writing it. So we discussed random walks on, first we discussed simple random walk on a graph where we have a graph, undirected graph. And what it does is from every point, we go equally likely to one of the neighbors. And later I defined a weighted, simple random walk on a, where is the weighted case? I thought I described it. Okay, so here the more general weighted case is where you put some edge weights on the graphs. Edge weights are some positive numbers, and Pij is not going to be equally likely, but with probability proportional to the weights. If you are vertex I, you go to one of the neighbors, but the probabilities will be proportional to the weights of those edges. Wij divided by sum over k adjacent to I, Wik. Okay, this is what weighted graph is. If you take the weights to be 1, you get back simple random graph, simple random walk. Okay, so what I want to now say is that, in fact, simple random walks on graphs and reversible chains are the same thing. They are just two names for the same thing. Okay, so how is that? Let's see both ways. One way we have essentially seen, though I did it only for simple random walk. Let us see it. So if we have, if x is random walk on this graph G, which is has vertex at V, edge at T, and edge weights W. So we are talking about only finite state spaces, okay, just for simplicity. So this is suppose random walk on this. Then you can take pi I to be, so it is reversible with pi I to be the, instead of the degree, earlier for simple random walk we found that sigma I was basically proportional to the degree. So here pi I will be not degree, but instead of degree we will have what is the generalization of degree to weighted graphs. It is the sum of the weights over all j adjacent to I. Okay, so let's give that, let's call that the generalized degree. Okay, uh, so let's call that the degree. I mean, it's not, it's degree in that sense, and then pi I will be just normalizing that. Right? Why is that? It's exactly similar to this. So because if you look at Pij, so here Pij is Wij over Di if j is adjacent to I. Otherwise it is 0. Right? Di now is this generalized form of the degree, sum of weights of edges incident to I. Now, if you take pi I to be, or you take di into Pij, what do you get? You get Wij. And what is dj into Pji? That is Wji. But that's the same. Edges are not directed. Weight of edge Ij and weight of edge Ji are same. Edges are undirected. So you see, this is reversible with respect to di's and hence with respect to pi. That's the, so what I'm saying is the generalization of what I said in the morning, that simple random walk is reversible with stationary distribution given by pi I proportional to degree. Here it is just proportional to the generalized degree. Okay, so this is one direction. What I have said is that random walk on weighted graphs are reversible. That's the conclusion is random walk on weighted graph is reversible. But converse is also true. So this the conclusion is random walk is reversible. Converse is true. Conversely, suppose x is reversible with respect to sigma. That means sigma I have some Markov chain on a finite state space such that, and this number sigma on the states such that sigma I Pij equal to sigma j Pji. for all I and j in S. Okay, suppose it is reversible. Then we can make a graph. Then create the graph. Something is wrong with the tablet. So then create the graph G with vertex set being the set of all states. Okay, and edge is all those ij, I adjacent to j if so if pij is positive. Okay, so here you notice that sigma is positive. Sigma is a strictly positive. Therefore, Pij positive if and only if Pji positive. If this is 0, then the right side is 0, so Pij has to be 0. So this is an undirected. So this is Pij is positive if and only if Pji is positive. Even if the values are different, one cannot be 0 without the other being 0. But now I have to also create weights. The weight should not depend on the direction of the edge. I should give the same weight for ij as ji. What weight will I give? Well, Pij itself is not right because Pij may not be equal to Pji. But here I have a quantity which is the same in both directions, sigma I Pij. So I define weight of the edge to be sigma I Pij, which is same as sigma j Pji, which is Wji, right? Let me put this in brackets. So now what I'm saying is if you start with a reversible Markov chain, you can create a graph with vertex set being the states, edges being all the allowed transitions, and weights being sigma I Pij. Then it's an easy exercise. Check that random walk on G is the same as the original Markov chain. Is the same as the given Markov chain, meaning it has transition matrix P. Because what does what does here, what is the transition? It should be weight divided by sum of weights. What happens when I sum this? So, well, okay, let me leave it as exercise. It's an easy exercise. Okay. So the point is random walks on graphs are special case of Markov chains. In fact, they are exactly what are called reversible Markov chains. That's the difference. Some chains are not reversible. I'll show you an example in the things that I had written. So here in the examples of Markov chains, look at the Setlin library. The Setlin library, we had n books, and each step is picking a book at random and moving to the front. This chain is not reversible for the reason that you can go from 2134 to 21 2134, we can go to 1342, right? If you pick 2 and put it to the end, you can go to 1342, but you cannot go backwards. From 1342 you cannot go to 2134 because you cannot bring a book to the front and go there in one step. So this is a not reversible Markov chain. So reversible Markov chains are a special case. They are exactly random walks and graphs, and they are particularly important. They have very nice properties. Okay. Any questions about this? That was one point. Point one I wanted to say. Second point, so this applies to reversible chains, but for simplicity, I will assume, so take any reversible chain. So this applies to what I am going to say applies to general reversible chains with some modification. But we assume we take a special case where sigma is a 1. That is, we assume Pij equal to Pji. That is, sigma I equal to 1, or pi is uniform on S. Pi gives equal probability to all elements of S. That's a special case. P becomes symmetric. Otherwise, I can modify this argument, whatever I'm going to give, but I want to convey the gist of it. One example to keep in mind, very important example, is simple random walk on a D-regular graph, where P is 1 over D times the adjacency matrix of the graph. Okay? A is the adjacency matrix. A is the adjacency matrix. That is one example. We know adjacency matrix is symmetric. The graph is undirected, so the adjacency matrix is symmetric. That is the special case. Okay. So what I want to say here is that, okay, so we know that P to the T ij converges to pi j. But what is the rate of convergence? That's what I want to. This is a very, very important and kind question also. What I'm going to say is the most basic point, but it is an important point which you may encounter in other situations. So I want to say this. So question I want to ask is, how close is P to the T I comma j to pi j? So yes, as t goes to infinity, it gets to there, but how fast? Okay, this is what we want to say. So for that reason, I will write the spectral decomposition. So let's write the spectral decomposition. Of P. Earlier I was writing it as xd x inverse. This is a symmetric matrix, so there is an orthogonal decomposition, right? I mean, there is a orthonormal basis of eigenvectors. But let me write it in a slightly different way. We can write it as lambda 1. So another way of writing it is V1 transpose plus lambda 2 V2 transpose plus dot 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 lambda n Vn transpose. Okay, so Vn, so V1, V2, Vn is an orthonormal basis for Rn. N here is the size of the state space. Okay, N is the size of the state space. And we have this spectral decomposition of this symmetric matrix. Okay, where also we know one more thing. What is lambda 1? We take to be 1. And then V1 is orthonormal. So it is the constant vector divided by square root of n. So as to make it to have norm 1. Constant vector has norm n. So we divide by square root n. And then other eigenvalues are all, since I am assuming irreducible aperiodic, we saw by Perron-Frobenius theorem, all the others are less than 1 for j greater than equal to 2. Okay, so this is the spectral decomposition of P. With this, we can now answer the question, how close is P to the T ij to pi j? Okay, so let's raise the matrix P to the T. What's the spectral decomposition of P raised to the power T? Suppose I raise P raised to the power 10. What happens to eigenvalues and eigenvectors? Well, eigenvectors remain the same. Eigenvalues become powers, corresponding powers of this one, right? So this becomes lambda 1 raised to the power of t v1 transpose plus lambda 2 raised to the power of t v2 transpose and so on up to lambda n to the power of t vn transpose. So that's just the eigenvectors remain same, eigenvalues change. But this has not changed. Lambda 1 is 1. So this is still, what is this? This is the, when I take v1 to be 1 by root n, so you notice that this matrix lambda 1 v1 transpose is the matrix with all entries 1 by n. Okay, so this matrix is the, I can write it as 1 over n times j. J is the all ones matrix. Okay, so this is what we get. Now lambda 2 to lambda n being less than 1, absolute value less than 1, their powers go to 0. That was the idea, right? So let's just write, for example, p to the t I comma j minus the corresponding entry here. Let's take this one to the other side. The corresponding entry is 1 by n, right? So is this whole thing equal to lambda 2 to the power of t v2 or v2 of I v2 of j. Okay, I mean the ith coordinate and jth coordinate and so on. So lambda n to the power of t vn of I minus vn of I vn of j. Now let's bound it by absolute value. The correct thing is to do something slightly different, but for the purpose I am doing, what the point I am conveying, I don't care. Let me just look at p to the t I comma j minus 1 by n. Now this will be small, but that may be because n itself is small and both of these are small. Let us even sum it over j. Okay. So when I sum it over j and fix I and sum it over j, what happens? I will get this is less than equal to, look at something like this. Put absolute values in all of these. Okay. So you'll get mod lambda 2 to the power t times summation v2 of I v2 of j. But that is, so if you look at mod v2 of I mod v2 of j, what is it? Over j, v2 of I, this is bounded by 1 because v2 is a vector of norm 1. So all the entries are bounded by 1 and summation v2 of j, you can say it is bounded by summation v2 of j square. Koshishwas will tell us that it is bounded by maybe square root of, so am I making a mistake? Square root n times square root of summation v2 of j square, right? So something like this. And this is 1. So you will get something like maybe I'm getting here square root of n or something like that. Plus, I may be making a mistake here. Sorry if I'm making lambda n to the t to square root of n. So what is it bounded by? It is bounded by, okay, so I don't really care about all this. Even if this is wrong, I don't care. What I want to say here is that maximum over k greater than equal to 2 of mod lambda k raised to the power of t. Okay. So if we look at this one, so here I can, this is true for all I, so I can write max over I also. So this quantity, how close it is, how small it is, so this is the distribution at time t starting from I, how close is it to uniform distribution, and it is saying that modulo some factors which I don't care, this depends on mod lambda k to the power t. It decays exponentially fast since all these are less than 1. So, but this is, let's write it as constant Cn into alpha power t, where let's write it as So look at all the. So we know that one is an eigenvalue and the other eigenvalues are inside the unit disk. So what we are taking is the maximum of that. So let's write it as alpha to the t, where alpha is the maximum over k greater than equal to 2 of mod lambda k. Okay. So the rate at which this decays exponentially fast. So this is decays exponentially fast as t goes to infinity. However, the rate depends on how close alpha is to 1. Okay, so what matters is the smaller it is, the better. Smaller the alpha, better it is. In particular, what matters is this S, which is 1 minus alpha, the gap between 1 and S. This is called spectral gap. Okay, the larger the gap, the faster the Markov chain converges to its stationary distribution. Okay, so that is where the interest in constructing graphs with large spectral gap comes. So this implies that larger the gap, better the mixing. Mixing means convergence to stationarity. Okay. So one question that came out of this is, so the construction of expander graphs, which is basically graphs, you want to construct a sequence of graphs which are increasing in size, n increases, such that the spectral gap remains bounded below. It doesn't become small. All the eigenvalues stay bounded away from 1. Now that is very easy to construct. If you take the complete graph, for example, the complete graph, one eigenvalue is 1 and all the other eigenvalues are 0, okay, or something like that, or one eigenvalue is 1 minus 1 by n and all the other eigenvalues are close to 0. So spectral gap is very large for complete graph, but the interest is in constructing sparse graphs. You fix the degree. Suppose I fix degree to be 10. Can you construct a sequence of graphs where each vertex has degree at most 10, let's say equal to 10, and the spectral gap does not go to 0? That is what leads to this business of expander graphs. Did anybody talk about expanders in this course?
No, Manjunath.
That is not come. Okay, so expander graphs are, say, d-regular graphs. D is fixed. So we want a sequence of d-regular graphs. D fixed, 3 or 4 or whatever, and n going to infinity. Okay, n is the number of vertices. So we want larger and larger graphs, but such that spectral gap, we want it to not go to 0, stays bounded away from 0. And how bounded away from 0 can you keep it? All those questions come. So there are many constructions of expander graphs. Easiest is to do some random construction, but deterministic constructions are not so easy. So it was first done by Margulis, the construction of expander graphs. But then how big can you make the spectral gap? That brings us to things like Ramanujan graphs and all these very interesting things which you may have heard about. So, but I will not go there. But the point is, all those are also important to the study of random walks. If you want random walks which converge to the stationary distribution fast, then you need to make sure that the spectral gap stays bounded away from 0. Okay. So that's the other second point that I wanted to make before going to the other topics. Any questions here? Okay. If not, then let me change tags. So if I lost you, maybe you can try to come back into this one, because this is a new topic. So the other questions. So one is the recurrence transients. Question, and the gambler ruin question, harmonic measure question. I don't know how much I will say about both, but recurrence transients question is actually, yeah, maybe I will just do the recurrence transients question. Let's see if I have time at the end, which I highly doubt. Uh, I'll come to that. Recurrence transients question. So first, let us take a finite irreducible Markov chain. Even that is interesting. So there is a, I mean, that's not interesting for this question, but we can start there. So again, let's take S to be S finite first to start with, and then P is irreducible aperiodic. Okay, so actually it's not needed, but let's just take it. Let's not worry about it too much. X0, X1, X2 is the Markov chain with this state space and this one. Okay, so some things that are of interest are very much of interest are, so you have this state space S here, and here you have a state, let's say I, and here you have a state J. Okay, suppose I start the Markov chain at I, will I hit J, and how long will it take me to hit J? So Tj is first time. Let's say t greater than equal to 1. Let me simplify and say t greater than equal to 1 such that xt equal to J. Okay, even if it starts at J itself, I want the next time I come back. Okay, so it is the first hitting or return time. Hitting or return time. So I say return time because if the random walks, if I equal to J, then we are asking, we are starting at J, what's the next time I come back to J? Okay, so that's the kind of question that is being asked here. And is it necessarily finite and so on? So the fact is, so if it's a finite Markov chain, then there is an easy argument that Tj is necessarily finite. Okay. Uh, I will not try to argue that. It is something that you can think about. I mean, so these are all done in some great detail in Markov chain class, but I don't want to spend too much time here. There is a simple point that you cannot avoid J. See, it's irreducible and aperiodic. You can use the fact that there is some time. So point is, so you remember that by Perron-Frobenius, we said that there is a capital T here. So okay, let me go back here. The Perron-Frobenius said that there is a capital T such that P to the T ij is positive for all ij. That means if you take T steps, let's say the minimum, okay, so maybe I will even give an argument, okay, so let me give an argument here why this is true. This type of argument is commonly used in Markov chains. So let's give a proof of this. See, there exists T such that P to the T I comma j is positive for all I comma j, right? So let delta be the minimum of it. P to the T I comma j, I and j in S Okay, so this minimum is also a strictly positive number. What does this mean? This means that, so you start the Markov chain. Okay, so you are starting, let's say wherever you are starting, my target is J. Okay, so it doesn't matter where I start. I look at T steps. Okay, so we declare success if it ends at J. At the end of that, I don't care what all it does in between. If you end at J, then you declare success. Then you have hit J, right? Then Tj is finite, meaning you have come to J. Suppose you fail. What has happened? Suppose you fail, then okay, the trajectory did not come to J. Maybe it did come in before, but I don't care. Suppose it is somewhere else. If fail, you are somewhere else, some state K. But from there again, give yourself another T steps. Okay, in the next T steps, there is a chance to come to J. Okay, so there is a success probability which is at least delta, right? Because p to the t ij, the minimum is delta, there is a success probability of delta in the first time. Give yourself another time, and again you have a success probability greater than equal to delta. And then you keep repeating, each time you have a success probability. Every time you give yourself T, capital T steps, and see whether you come to J at the end of it. Each time you have a delta probability of success. Now, what you are doing is you are tossing a coin which has a delta probability of falling heads. Can it never, is it possible that you never get a head and always get tails? Eventual success is 1. Why? What's the probability that I fail some 100 times? Well, each time I have to fail. To fail means to fail every time. So 1 minus delta times 1 minus delta times 1 minus delta, like that to the power 100. So if you give yourself enough chances, the probability of failing every time is 1 minus delta to the power of the number of times, and that goes to 0. That means eventually you will succeed. So by giving yourself enough chances, you will eventually succeed. So Tj is finite. So what this means is that the random walk will come and hit every vertex. So this means that starting from any I, Tj finite, that probability is 1. So this is what we mean by saying the random walk is recurrent. Wherever you start, you do hit the state J. Whatever state J you want and whatever starting point I you take, you are sure to hit J eventually. That is what what this is. Okay. Any questions on this? I don't know if I'm going too fast. It's not clear what it is. Okay. Uh, I want to say one more thing. So this is just a qualitative thing saying that Tj is finite. You will hit, but how long does it take to hit? In fact, one can show that if you start at state J, what is the time it takes to return to state J? Okay. So suppose I start at some state in a, let's say, random walk on a graph, you start in a vertex. What you wait till you come back to the same vertex next time. What is the expected time? So this means this is the expectation. This means the expected time Tj given that x not equal to j. Given that you started at j, what is the expected time to return? Okay. So the nice fact, which in the interest of time and not to not say too much, I will just put it here. It's a very interesting point that this is exactly equal to 1 over pi j. The reciprocal where pi j is the stationary probability. Okay. So the higher the stationary probability, the sooner you come back, right? And the lower the stationary probability, the later you come back. So this is reciprocally related to the stationary probability. If you have a small stationary probability, expected time to return will be high. And if you have a large stationary probability, expected time to return will be small. So this is a very interesting point, and this is not too difficult to prove, but Markov chain books have it. Now I will not spend time to do it, but it is an interesting point that the expected time is this much. Okay, the reason I brought it up is it relates to one of the things I mentioned about the Ehrenfest chain. So let's look at the Ehrenfest chain. It would have been nice to write a formula for expected time to hit j starting from I, ei of tj, but I don't, there is no simple formula for that. So I will only write this one. So let's look at the Ehrenfest chain where we have states 0, 1, 2 up to capital N. Okay. So one of the things where you remember that the interpretation of this is that there is a partition in this and there are gas molecules on both sides, and the state is how many molecules are on the left side, which can be total of n molecules, and each time one molecule is picked and it will move to the other side. Okay, so that is the state spaces. S is 0 to n. This indicates how many molecules are on the left partition, in the left partition. Now let's look at what the meaning of recurrence is. Okay, recurrence means every state will occur for sure. Okay, now that means that you imagine this as a big room, and this is the left half and this is the right half. Whichever room you are sitting in, this is the left half, this is the right half. What this tells you, what recurrence tells you, is that every state is going to be visited. Means whatever n is the number of molecules of air, let us assume that this requires the room to be completely closed, no air comes in, no air goes out. Okay, imagine that situation. But even then what it says is that it will visit every state. What does it mean to say every state? There will come a time when there are no molecules on the left half and all the molecules are on the right half. There will also come a time when there are all the molecules are on the left half and no molecules on the right half, right? Because this is what it says. But nobody has ever seen that happen. Has it ever happened that in your room, one half is completely empty of air and the other half is full of all the air has moved to the other half? This never happens, although here we have proved that eventually you will hit every state, so it must be possible to happen. How this was a big puzzle in statistical mechanics in late 1800s, that this is a contradiction to the postulates of statistical mechanics. Something must be wrong is what some people said, because if this was true, then we should see occasionally that all the molecules in the room move to the right half or the left half, and but we don't see that. Now actually there is no puzzle in this. The reason is, I mean, there is no paradox in this. The reason is we just have to remember, so recall here that pi j is 1 by 2 to the n is the binomial distribution n choose j. Okay, pi j is 1 by 2 to the n choose j. So one small thing, so pi 0 is how much? 1 by 2 to the n. Let's also write pi n by 2. Pi n by 2 is 1 by 2 to the n of having half of the molecules. This is n choose n by 2. Imagine n is even number. Now this one can check that this is like 1 by square root of n. Okay, so this you can get by what is called Stirling's formula, which I will not go into now. So the probability that exactly half of the molecules are on the left, half of the molecules are on the right is 1 by square root of n, which is a very small number. Here really we should think of as n as something like 10 to the 24 or something like that, right? Because you know Avogadro number, there are 10 to the 23 molecules in every mole of gas. So in a room, there are something like 10 to the 24 or more. Okay, 10 to the 25 or whatever number of molecules. So let's take n to be 10 to the 24. Now pi n by 2, probability of having exactly half on the two sides is 1 by 10 to the 12, which is small. But it is nothing as small as 1 by 2 to the n, which is 1 by 2 to the 10 to the 24. This is exceedingly small. Okay, this is small, but this is even smaller. So what that means is, let us say, let's look at the expected time to return. Suppose you start in a state where you had no molecules on the left. How long does it take to come back? According to our this one, the time or the number of steps is 1 over pi 0, which is 2 to the power of n. Whereas if I start with half of the molecules on the left, half of the molecules on the right, and I look at the next time I come back to the same state, that is square root of n. Okay, so this is like 10 to the 12, and this is like 2 to the 10 to the 12, 10 to the 24. What is the difference? This is a huge difference. So this is steps. This is how many steps it takes. Let's say in 1 second, 1,000 steps take place. Okay, even then, this will mean that 10 to the 9 seconds later, you are back to that state. Okay, 10 to the 9 seconds is not that far away. Okay, it happens soon. But this one is how many time, how much time? 2 to the 10 to the 24. Okay, that is divided by 1,000. That many seconds you need. This is larger than the time of the universe. Larger than the time of the universe or age of universe or something like that. That means the fact that you did not see this happen should not be is not anything against the theory, because the theory is telling you, yes, it will happen. You will come to the state where there are no molecules on the left, all the molecules are on the right, but it will take 10 to the 10 to the 24 steps. That means you don't expect to see it. So there is no problem in the theory. Okay, so this was a resolution given by this Markov chain of a very fundamental puzzle in statistical mechanics. In any case, this is an interesting point which is explained by this. So I thought I would explain this. Okay, any questions on this?
Hello, sir.
Yes.
Yeah.
Yes.
Is there a chain you can show on a graph which is irreducible,
Huh.
yet not reversible? What's the latest term? Really?
Periodic or what?
No, this latest term. What was it?
Reversible.
Yeah, yeah.
No. Sorry, I don't know. Which term do you mean? I can go to the previous page.
Latest definition. No. Latest definition was what? No, the latest definition you made.
The hitting time. You mean these ones?
Recurrent. Something that is
Recurrent. Sorry. Recurrent. Yeah.
something that's irreducible yet not recurrent.
Well, what I have shown just now is that, in fact, yeah, I actually assumed aperiodic. Aperiodic is not strictly necessary here, if that's what you're asking. Any finite state chain which is irreducible is recurrent. The argument I gave is for aperiodic, that's all. The argument I gave is aperiodic, but it is not required. Even if you remove the aperiodic condition, if you have a finite state irreducible chain, then it is recurrent. Okay, so that's, I think, what you are asking. There is no.
Right. So how is how are the two definitions different?
Which one? I mean, here I assumed aperiodic just for extra simplicity. Any irreducible finite state.
So irreducible means there's a possibility that
Yeah,
we can go from state I to state J,
right.
and recurrence guarantees that. Is it something?
No. Recurrence is guaranteed by that. If there is a possibility for finite state, if you have finite number of states, and there is a positive probability to go from any state to any state, maybe in 1,000 steps, in million steps, doesn't matter, then whatever you start, you will visit every state. And one can argue that you will visit every state infinitely many times. But here I just showed that wherever you start, you are sure to hit state J, whatever be J.
Oh, I see. That means if there's a possibility, you're sure to
Yeah.
that it will
If there
surely
is
happen.
a possibility and you give yourself enough time, then it will happen.
Oh, so maybe the difference occurs only in infinite states, is it?
Exactly. That's what I'll come to. That's the last topic I will do. In the finite state space, recurrence is not an interesting question in the sense it is trivially true. Well, it need not be recurrent because just because two pieces are separated, maybe we have two pieces of the graph which are disconnected, then there is no way you can go from here to there. So then it won't be recurrent. But modulo the triviality, finite state space chains are always going to be recurrent. So recurrence is not an interesting question. What is interesting in the finite situation is to do it quantitatively, like here. Not just ask will it hit, but when will it hit? How long does it take? That would be interesting in finite state space. But whether it will hit is trivially true. Okay. So what is interesting is in infinite state space, even that is not guaranteed. Okay, now let's come to the infinite state space. There, it is no longer guaranteed that we will hit. Okay, so now let S be countably infinite. And P, we can still assume irreducible. Meaning, you will actually you can go from any state to any state. Okay, aperiodic is not needed here for the purpose at hand. So X is the Markov chain. So the question that I want to ask is, suppose I start at some state I, is it true that I will hit J eventually? So if this is true for all I and J in S, then we say the graph is recurrent. The Markov chain is actually this is true, but I will only take, I mean, there are many small reductions which it is not appropriate to get into in this short course. So I will just take, starting from I, will I come back to I? Okay, both ways can be asked. This makes no difference whether you take I and J for all ij or you take only ask for return from I to I. Both will give you the same answer. Anyway, so what I mean is it's the same as Pi, Ti finite is 1 for all I. Instead of taking two states, you take one state and ask, will I come back to it with with probability 1? So then we say the Markov chain is recurrent. Otherwise, we say it is transient. We say it is transient. Transient means that doesn't mean you don't come back. This means there exists I such that Pi Ti finite is less than 1. Okay. So it means that you can come back, but you may not come back. That's the point. There is a chance to escape. That's what the question is. Again, there are lots of reductions. Here I reduced from I to J to single state, but this is actually equivalent to Pi Ti finite for some I. if the chain is irreducible, if it is true that from one particular state you come back with probability 1, then you will come back from any state to itself and from any state to any other state. So these are all just simple reductions. I hope the definition of recurrent and transient is clear. So you have, let's say, think of the case of graph. Maybe I'll just write here the case of Z2, which is what I explained as Polya's original motivation. We considered the graph Z2. So you are starting a random walk, which means you wherever you are, you go to one of the neighbors with probability 1/4, then go to one of the neighbors with probability 1/4, and so on. Question is, suppose I start at the origin, will I come back to the origin with probability 1, or is there a positive probability to escape? That is without coming back. Okay, so be careful. I am not asking whether it will escape with probability 1. That's not true, because you can go one step here and come back. So there is at least probability 1/4 into 1/4 to come back. Right? So there is always a chance to come back. Question is there a chance to not come back? Then you would call it transient. And if there is chance is 1 that you will come back, then you call it recurrent. Okay. So how do we decide such questions in terms of the original transition matrix? That's the point. Okay. Is the question clear, or is there any question about the question? Okay. So the fact is, so the theorem here is, I think this is the first time I'm writing the word theorem. I gave 4 lectures without writing the word theorem a single time. Okay. Though I did give theorems, but okay. So theorem is that, so Markov chain is recurrent if sum over t from 1 to infinity, 0 to infinity, it doesn't matter. P ti comma I is, sorry, equal to infinity for some I in S. It is same as for all I in S. Okay, it's enough that, but let's not worry too much about that. So Markov chain is recurrent if and only if this series, you take p to the t I, that should be infinite. And of course, this itself says it, but to iterate, let me say there are only two possibilities, recurrent or transient. So this is if and only if, sorry, if and only if. Okay, maybe I'll just write IFF. This is an if and only if condition. So transience also has an if and only if condition, which is the converse one. T equals 0 to infinity, PTII is finite for some I in S, which is same as for all I in S. It's enough to check for one of them. It's the same. So recurrence transients can be calculated by taking p to the t I. Now P is an infinite matrix, but P to the T I hope it makes sense. This is the return. This is the probability that xt equal to I given x0 equal to I, right? That's what I mean. So we saw that. So if you are worried about infinite matrices and taking their powers, what I mean by PTII is just probability that if you start at I, after t steps, you are again at I. So if you can show that sum is finite or infinite, then you can tell whether the Markov chain is transient or recurrent. Before going to give any argument for this, let me work out an example. So let's do the example of Z. simple random walk on Z. Okay, take I to be the state 0. Okay, so what does simple random walk on Z look like? So here we are thinking of 0 as the starting point, and there are all these states 1, 2, 3, and so on, -1, -2, and so on. And each time you go to the right or left. Okay, so now let's allow ourselves. Okay, let's do half of probability. Let's do half of probability on each side. So what is the return probability? So then what is p to the t 0, 0? My question is, if I do this, so what is, just for simplicity, in 2 steps, what's the probability I come back to the origin? Suppose I start at the origin. What's the probability after 2 steps I am back at the origin? How do I calculate that? Anyone has a suggestion for this? We will need more generally, but we should be able to tell this. In 2 steps, if I start the random walk at the origin, what is the probability after 2 steps I am back at the origin? Yes? Okay. So to come back to the origin in 2 steps, I have to go, either I have to go from 0 to 1 and back to 0, or I have to go from 0 to -1 and back to 0. Okay. So there are 2 ways. So this will be half into half plus half into half. So it is actually 1/4 into 2. So what about P300? What is the probability starting at 0? I come back exactly, I mean, it's not the first time or anything. That after 3 steps, what's the probability I'm back at the origin? Yes, anyone?
It would be 0.
It is 0 because it's not possible. Because it is a periodic chain, it cannot come back in 3 steps. But P400 is possible. So I have to come back in 4 steps. How is it possible? Now I'm not saying it's the first time. You may have come back before, but after 4 steps, you have to be back at the origin. How many ways are there? What is that probability? Okay, so this is what we are trying to find out. So let's just do it in general. So let's do the easy case first. 0 if t is odd. Right? Because you cannot come back in odd number of steps. But suppose t is 2s is even. Let's write t as 2s. Now in 2s steps, in 20 steps, you have to come back to the origin. What does that mean? You started at origin. After 20 steps, you came back to the origin. That means you must have taken 10 steps to the right and 10 steps to the left. That's the only way you can cancel, right? So to do this, you have to take 10 steps to the right and 10 steps to the left, and it does not matter in which order you take them. So if in 2s steps I have to come back to origin, I have to take s steps to the right and s steps to the left. But how many ways can I choose out of 2s steps? Which steps are right? I can choose in s ways. Okay? That is 2s choose s where different paths are there. So for example, I can take all the s plus steps and then all the minus steps. Or I can alternate them, plus minus like that. There are 2s choose s different ways in which I can come back to the origin. But each of those trajectories, since each step has probability 1/2, it is 1/2 raised to the power of 2s. Okay? 2s choose s by 2 to the 2s. So if in 20, if s is 10, that means in 20 steps, you have to take 10 steps to the right, which can be any of those 20. So 20 choose 10. And then each trajectory has 1/2 to the 20 probability. So that's what we get. Okay, so this is what PT00 is. Now we have to determine whether that sum is finite or infinite. Can we do that? That's the question. Any questions about this probability, return probability? So here I already wrote this 2s choose s by 2 to the 2s. If you use Stirling's formula, so this asymptotic means ratio goes to 1. It behaves like 1 by square root of s with some constant. See, what I need to do is to determine, I don't need to find the sum. I only need to know whether the sum converges or diverges. Okay, so for that, you know from basic analysis class, to determine whether something converges or diverges, you don't have to work with the exact numbers. If you replace it by some other numbers, this asymptotic means ratio goes to 1, right? You know things like this. If an by bn goes to 1, then summation an converges if and only if summation bn converges. Right? This type of ratio test and other things, comparison test, all these you know. So if 2s chooses by 2 to the 2s behaves like 1 by square root of s, then when I do this sum, what do I get? All the odd terms fall out and I am left with only the even terms. So the sum pt 0 0 t equals 0 to infinity, first place it is the same as sum over s equals 0 to infinity p 2s 0 0, because anyway all the odd terms vanish, and then since this is like p 2s 0 0 is like constant over square root s, so the question is what happens to 1 by square root s or constant by square root s? Does it converge or diverge? Does it converge or diverge? 1 by square root of s sum. Yeah, you must know this, right? So what happens to the 1 by s to the power p? 1 by n to the power p, n equals 1 through infinity. When does it converge?
P greater than 1.
When p greater than 1, and it is infinity for p less than equal to 1. That's what it is saying. So here n is replaced by s, that's all, but the power is half. So this series diverges. Therefore, the original thing also diverges. Because it is comparable to this one, and if that sum diverges, what does that say? The Markov chain is recurrent. Simple random walk on Z is recurrent. Okay. So this is an example of a chain which is recurrent. Okay. So in the same, we can do another one. So let's take a random walk on Z. So I am taking S to be Z. Except that now the transition probabilities I change. Pi plus 1, let us say, is P, and Pi I minus 1 is 1 minus P. Okay, P is fixed. Let's say this is 3 by 4 and this is 1 by 4. Okay, so just for specificity. So in this Markov chain, we are going to the right with probability 3/4 and to the left with probability 1/4. Now what happens to P to the T? So is this random walk recurrent or transient? Suppose we want to do the same. This is also a Markov chain where the transition probabilities are not half and half, but 3/4 and 1/4. What happens to p to the t is 0, 0? Again, if t is odd, you cannot come back in an odd number of steps. But if t is even, then how can I come back? Previously, I had 2s chooses different paths which came back. They will be the same paths. If you have to come back in 2s steps, you have to take s steps to the left, s steps to the right. Only the difference is every path had 1 by 2 to the 2s probability. Here, you have taken 3 by 4, I mean, s steps to the right and s steps to the left. Okay, so this thing is actually 2s chooses 3 to the power s by 4 to the power 2s. Okay, so this is what we have. So the thing has changed slightly. This was 2s chooses 1 by 2 to the 2s, and this is 2s chooses 3 by 4 to the power 3 to the s by 3 by 4 to the s, 1 by 4 to the s. Now it's an exercise. Let me just leave it that P00 2s is bounded by an exponentially decaying quantity. Okay, so this is actually 2s choose s is like constant over square root s times 2 to the 2s. That's what we said earlier. 2s choose s by 2s choose s by 2 to the 2s behaves like constant over root s. So what does that mean for 2s choose s? 3 power s by 4 power 2s. How does that behave? Well, let's write it like this. C by root s. Here I have 2 to the 2s, and then I have 3 to the s by 4 to the 2s, which is, well, this is 4 to the power s, 4 to the 2s. So this becomes c by root s into 3 by 4 to the power of s. See, the difference is earlier I had c by root s. Now I have an exponentially decaying quantity. Okay, so P2s00 behaves like 1 by s is not the important term here now. Now the constant by root s is there, but the more important term is 3 by 4 to the power s, which decays to 0 very, very fast. And that sum is finite. You don't even need the square root s. This is finite because a geometric series converges. Hence, this random walk is transient because the sum is infinite. According to this criterion, that random walk is transient. Because so if you have 3/4 probability to the right and 1/4 to the left, you will not come back. I mean, with probability 1, with positive probability, you will just escape. Okay, so this is how you can use this theorem to determine recurrence transients, provided you can calculate the exact transition probabilities, then you may be able to do. I showed it only for two different random walks on Z, but you can do it on Z2 and Z3. It takes a bit more time, which I don't have, so I will not go there. Okay, so this is how you determine the. So for Z2 particularly, it is doable. Okay, so this is not a trivial exercise, but let me leave that as a somewhat non-trivial exercise for those of you who are interested. Show that simple random walk on Z2. That means 1/4, 1/4, 1/4, 1/4 probability is recurrent. Okay. In fact, on Z2 also you can show it is recurrent. On Z3 it is transient. That is the non-trivial theorem of Polya. And we don't have time for that. So I mentioned several questions. So, but anyway, so this is a short course. So, and I tend to go slow. So I didn't cover all of them. going back, what were the questions I mentioned? I mentioned three questions. First was the long-term behavior of a Markov chain. Second was the recurrence transience question. And third was the gambler's ruin problem. Now, I did not come to the gambler's ruin problem at all. But I did the long-term behavior in quite detail. This is the most important of the questions. And I have given you a kind of glimpse into the recurrence and transience question. Okay. Okay. I think I'll stop here. And if there are any questions, I'm happy to take them. Okay, so if there are no questions, then I can stop sharing here.
Manjunath, what about the infinite analog of this Ferran-Rubinius theorem and the state theory distribution and all?
Well, okay. So I don't know if one does it by an infinite analog of Perron-Frobenius, but one can do slightly other methods. One can there is a way to show the existence of stationary distribution, etc., by somewhat more probabilistic methods. You can say there's a different expression one writes, and one can solve using that. I mean, one can show the convergence to that. So one can show, let me just go back here. Oh, sorry, long-term behavior. Yeah, here, oh, sorry. Third one. Right. So here the pi came from this Perron-Frobenius theorem. But this is actually true even in a irreducible infinite Markov chain, but there are some subtleties. You don't always have stationary probabilities. So some Markov chains don't have stationary probability measures. Meaning pi can exist, but p to the t ij, I mean, what may happen is that there may be you need what is called positive recurrence. So with infinite state spaces, there are some subtleties where this may not actually happen. P to the t ij may just go to zero for all ij. That can happen. For example, if you take simple random walk on Z, that's what happens. P to the t ij will just go to zero for every ij. But there are certain chains where you have what is called positive recurrence, which means this expected time to return is finite. Okay, so positive recurrence means so suppose you have an infinite state space. Let's say irreducible, P is irreducible, and let's say aperiodic. Then, so we say that it is positive recurrent if expected time to return is finite for all j. Okay, if it happens for one, it will happen for all. So if that expected return time is finite, then we call it positive recurrent. And then if that is the case, then you can just take the reciprocals of them, and that will give you the stationary probabilities. Problem is when these are infinite, pi j will be just 0 and ptij, this happens, and ptij converges to pi j. All this happens. But these methods I know are not matrix theoretic, so I did not want to talk about this. I wanted to give the graph and matrix methods here. For those, we usually use other methods, probabilistic methods somewhat.
Okay.
Yeah, I'm not sure if there is any kind of Perron-Frobenius type. There are some infinite dimensional Perron-Frobenius, but not this one. I'm not sure if it comes from any of those.
Okay, thank you.
Sure. Okay. Okay, so then